Hello AP Physics 2 students, here's your rapid review for Unit 2, Thermodynamics. Quick summary, energy transfer in gases can do measurable work on large objects. Thermodynamics is the study of heat energy and how it gets transferred. It's different from the other topics in this book or in this class because the systems focused on are, for the most part, molecular. So one of the things that we will try to do is connect what we're learning back to the molecular level. Since molecules and gases are at the heart of thermodynamics, this chapter introduces a lot of material introducing them. Key ideas. The behavior of molecules gives rise to the thermal matter or the thermal behavior of matter. First, internal energy is the energy possessed by a substance due to the vibration of molecules. Oops, I don't need this bullet point here. A substance's internal energy depends on its temperature. So internal energy depends on temperature. Down here, we've got a formula relating internal energy to temperature. Next, heat is the transfer of thermal energy. Heat is transferred by conduction, convection, and radiation. Conduction is touching. Convection is through a fluid, like warm air can transfer heat. And radiation is energy transferred through EM waves, like heat from the sun is radiation. When an object's temperature increases, it expands. The ideal gas law connects four important thermodynamics variables: number of gas molecules, gas pressure, temperature, and volume. So here is the ideal gas law. By the way, the first way that we write it is the one we use the most often. Here N is 8.31 and here N is the number of moles and R is 8.31. Let's see, where were we? Kinetic theory explains how the random motion of many individual molecules in a gas lead to measurable properties such as temperature. The first law of thermodynamics is a statement of conservation of energy. It is usually applied when a gas's state is represented on a pressure versus volume diagram. Oh, sorry, I've got a few typos here. From a PV diagram, internal energy can be determined using the ideal gas law and the pressure volume graph. The first law of thermodynamics is a statement of conservation of values from the diagram's axes. Work done on or by the gas can be determined from the area under the graph. We'll look at some examples in a moment. Heat added or removed from the gas cannot be determined directly from the diagram, only from the first law of thermodynamics. And we may recall that the first law of thermodynamics is delta U equals Q plus W. Let's see. Absolute zero is where all molecular vibrations stop and a gas would have no pressure or volume. Some of these formulas you are unlikely to see, but I will highlight kinetic energy. We'll remind you of kinetic energy. We also, in this unit, saw momentum. So I'll just write down the formula for conservation of momentum in an inelastic collision. Let's see. Work done by a gas is negative the pressure times the change in volume, and then we've got a rate of heat transfer equation. This rate of heat transfer equation, remember, refers to the idea that if I had a solid substance like a window or a door, and if I had a temperature on one side and a different temperature on the other side, that the heat transfer, so Q is heat per unit time, or the rate of heat transfer, equals the thermal conductivity, which is different for different substances times the cross-sectional area times the change in temperature, which would be the difference in the two temperatures, divided by L, where L is the thickness of the substance. Okay, let's review pressure volume graphs. So if we have a given amount of gas inside of a cylinder, and the cylinder has a piston, so the piston is free to move up and down. If we have a pressure versus volume graph, if we have a point on that graph, we can read the pressure and the volume right off the graph. If we have P1, V1, and N, we can figure out the temperature at that point using the ideal gas law. Another thing we should realize is that temperature is maximized when PV is maximized. This product of P times V is proportional to temperature. So maximizing PV will maximize temperature. Okay, another thing we looked at were some shapes on a pressure volume graph. If you see a shape that looks kind of like that, a hyperbola, it may be an isotherm, meaning constant temperature, meaning that delta U is 0. The change in internal energy is 0. If you see two curves and one is steeper than the other, the steeper curve is probably adiabatic. Alrighty, let's see. More about PV diagrams. The area surrounded in a PV diagram is the work. And I can calculate it by simply calculating the area of that rectangle, or I could take the area that I've designated in pink, and I could subtract off this area designated in blue. What else do we know about graphs like this? When the gas is expanding, that's work done by the gas. When the gas is contracting, that's work done on the gas. It has more work being done by the gas than on the gas. And when work is being done, when the net work is being done by the gas, that is a heat engine. Conversely, if we have a cycle going in the opposite direction where we have work being done on the gas and work being done by the gas, and here the network is on the gas, that's going to be a refrigerator. And this way around is clockwise. So heat engines are clockwise, and a refrigerator is counterclockwise. Or the cycle is counterclockwise. Okay, some other things about PV diagrams. Here's a summary. So isobaric means constant pressure, and number 1 here down below is an example of an isobaric process. Number 2 is now I've confused myself here. Constant volume. I don't think these pictures are right. Oh, number 2, sorry. Number 2 is adiabatic. I was reading the wrong thing here. Number 4 here is isobaric, meaning constant pressure. And Number 3 here would be an example of an isothermal process. And then we have a summary of what happens with work and internal energy. For example, in an adiabatic process, no heat is exchanged, so Q is 0, and therefore the change in internal energy is equal to the work. Finally, let's review entropy. Entropy is a measure of disorder. A neat, organized room has low entropy. The same room after your 3-year-old brother plays tornado in it has higher entropy. These are the quantitative measures of entropy, but these are not important for the AP Physics 2 exam. What you do need to know is that entropy relates to the second law of thermodynamics. In fact, we can state that law as follows. The entropy of a system cannot decrease unless work is done on that system. That means that the universe moves from order to disorder, not the other way around. For example, a ball of putty can fall from a height and splat on the floor, converting potential energy to kinetic energy and then to heat. The ball warms up a bit. Now, it's not against the laws of conservation of energy for the putty to convert some of that heat back into kinetic energy and fly back up to where it started from. But does that ever happen? No. The molecules in the putty, after hitting the ground, were put into a more disordered state. The second law of thermodynamics does not allow the putty's molecules to become more ordered without work being done on the system. Another example, a glass can fall off the shelf and break, but to put the glass back together, to decrease the entropy, someone has to do work. If heat flows into a system, the molecules will vibrate around more, causing an entropy rise. I don't know why there's a question mark there. When heat flows out of a system, the molecules become more ordered and entropy decreases. For example, a refrigerator does work to transfer thermal energy from the food you place inside and deposits this thermal energy into the kitchen. The entropy of the food decreases because it's getting cooler, while the entropy of the kitchen increases. All right, that is your rapid review.